Analyzing f prime and f double prime, finding intervals of increasing, decreasing, concave up, and concave down on f of x. Before we get into the calculus aspect, let's do a review example from pre-calculus. Given the graph of f of x, find the intervals where f of x is increasing, f of x is decreasing, f of x is positive, and f of x is negative. So here we have our graph, and we want to remind ourselves that this is the graph of f of x, the original function. And we want to describe the intervals where f of x is increasing. So when I look at this graph, I want to determine where from left to right the y values are getting bigger. So I'm going to go ahead and highlight those intervals where from left to right my y values are getting bigger, therefore increasing. When we describe intervals of increasing and decreasing, they are always open intervals and they are always x values. So we're looking at the interval from negative infinity to negative 2 being one of the intervals where f of x is increasing. So I'm going to write that as all x values in the interval from negative infinity to negative 2. And then we also have another interval where y values are getting bigger, and the x interval where that occurs is from 0 to infinity. So our second interval here would be all x values on the interval from 0 to infinity. Again, intervals of increasing and decreasing are just by definition open intervals, so open parentheses. One of the common mistakes that happens on a problem like this is that students will try to describe this interval using y values instead, because their eyes are drawn to this negative 4 right here. So they'll say that the function is increasing from negative 4 to infinity, but unfortunately that's incorrect because we have to use x values to describe intervals where the y values are increasing. And another mistake, and it's a very subtle one, is to write the answer like this. So to put x values in the interval from negative infinity to negative 2 union 0 to infinity. So this union symbol adjoins these two intervals together. So what you are saying here, if you were to put this, is you would be saying that over this entire collection of x values, the y values are just constantly getting bigger and bigger and bigger and bigger and bigger. Well, let's think about that. So from negative infinity to negative 2 on the x-axis, the y values are getting bigger and bigger, and the y values get all the way up to 0, because we're at the x-axis here. But then, when you jump over to this adjoining interval now that starts at 0, the y value is negative 4. So my y value isn't getting bigger and bigger and bigger across these two intervals, but over each interval, the y values are getting bigger, which is why I'm writing them separately. So it's a subtle point, but an important one. And then the second question is, where is f of x decreasing? So f of x is decreasing in between here. So from left to right, my y values are falling from negative 2 to 0. So we have x values between negative 2 and 0. Again, always open intervals. The second two questions are asking, where is f of x positive and where is f of x negative? So where is the function positive is like asking, where are the y values positive? So let's erase what we have so far, because this is a totally different question. So we're being asked, where is the function's y values positive? Well, that's like asking, where is the function above the x-axis? Because that's where y values are positive. And we again describe this collection of points using the x interval where that occurs. So where is the function above the x-axis beyond 1? So not at 1, because at 1 the function is equal to 0, which is not positive or negative. So we have to say that it's happening beyond 1, so that would be x values in the interval from 1 to infinity. So we're not going to be including 1, we're going to put open parentheses because the function is not positive at 1, it's 0, which is neither positive nor negative. And then where is f of x negative? So f of x is negative where the function is below the x-axis. So I'm going to go ahead and highlight that region. And I tried to show that I'm purposefully excluding -2. So at -2, that's where the function is equal to 0, which is not positive nor negative. So I want to know where's the function strictly below the x-axis. And I'm going to describe that again using x intervals. So we're going to describe that as x values in the interval -∞ to -2, not including -2. But then I want to pick right up after -2 and go all the way to 1, not including 1, again, because 1 is equal to 0, not positive or negative. And this time, we actually can use the union symbol here, because again, this is adjoining the intervals, and it's saying that the function is negative across this whole entire collection of x values. And that's true, that's accurate. So from -∞ to -2, I'm below the x-axis. From -2 to 1, I'm also below the x-axis. So this question involved no calculus. We were given the graph of f of x and being asked questions about f. Where is f increasing and decreasing? Where is f positive and negative? So we could strictly just look at the graph for face value to determine these quantities. So now let's take a second and try to introduce the concept of derivatives. Alright, so here's my function, again, my f of x, and what we want to do is sketch a few tangent lines on increasing intervals of f of x. So we said the increasing intervals were here from -∞ to -2, and here from 0 to infinity. Those were our increasing intervals of f, and we want to just sketch a few tangent lines on those intervals. So we're going to just pick some random points on the line and then sketch some tangent lines there. So just lines that are going to sort of barely graze the surface at different points. Whoops, there we go. And then maybe over here we'll pick a point and we'll draw our tangent line. And over here. And then let's say right here. I'm going to do my best a little bit to draw some tangent lines. Now, the question here is, what do you notice about their slopes? Well, if I focus on the slopes of these tangent lines, what I want us to observe is that all of these slopes are positive. So we had a function f of x. We observed that on the increasing intervals, that anytime I draw a tangent line, the slope of that tangent line is positive. So now we're going to go ahead and formalize an idea that relates the slopes of tangent lines, which is the derivative, and how that relates to the behavior of f of x in terms of increasing and decreasing. So what exactly does f prime of x, the derivative, say about f of x? Well, let's assume f of x is a differentiable function on the open interval from a to b. Then f of x, the original function, is increasing on the open interval from a to b if f prime of x is greater than 0 for x in the interval from a to b. So in other words, if slopes of tangents are positive, because the derivative is the slope of a tangent line. So what this tells us is for a function f of x to be increasing on an interval, that's only going to happen if the derivative, the slopes of tangent lines, are greater than 0, are positive. And then similarly, f of x is decreasing on the interval from a to b if f prime of x is less than 0 for all x in the interval from a to b. So this time, slopes of tangents are negative. Now before we start doing some computational problems, I want us to take a look at where might f of x change from increasing to decreasing or decreasing to increasing. So I want us to take a look at this graph for a second. This is the function f of x. So here I can observe that the graph is changing from increasing to decreasing, and then decreasing to increasing, increasing to decreasing, and decreasing to increasing. So if I focus on those specific points where that change is occurring, and I'm just going to sort of mark those points in red there, what I want us to observe is that each of those points would have a tangent line that is horizontal. And if the tangent line is horizontal, then the slope of the tangent line is 0. And that means that the derivative is 0. So where might f of x change from increasing to decreasing or decreasing to increasing? Well, when f prime of x equal to 0. It's possible. It's not required, but it is possible for f to change from increasing to decreasing or decreasing to increasing when the derivative is positive. Well, where else might it happen? A change from increasing to decreasing or decreasing to increasing might happen where f prime, the derivative, does not exist, and potentially any places of discontinuity. So let's look at some graphical examples of that. On this function right here, there is a change from increasing to decreasing. I can see that, I can observe that at this point right here, but the derivative does not exist there. This is considered a cusp, and so the derivative does not exist there, but that's a place where f of x changed from increasing to decreasing. Same thing with this example over here, y equals x to the 2/3. There is a change from decreasing to increasing at this cusp. So that's considered a place of non-differentiability where the derivative doesn't exist. We can switch between increasing and decreasing. And then in these two examples down here, I have examples of different types of discontinuity. I have a jump discontinuity occurring at A, so there's a change from decreasing to increasing at this discontinuity. And then also here there's an infinite discontinuity, a vertical asymptote, and my graph is changing from increasing to decreasing there. So this is the collection of places where f of x might switch between increasing and decreasing, where the derivative is 0 and where the derivative does not exist, and again, any places of discontinuity. So thus, f of x can switch between increasing and decreasing at essentially critical values. That's what we're describing here. Critical values, so the derivative is 0 and does not exist, but additionally, any x value excluded from the domain is also a place where a switch can happen from increasing to decreasing, such as vertical asymptotes or jump discontinuities. Let's take a look at our first example. Find the intervals on which f of x equals 3x to the 4th minus 4x cubed minus 12x squared plus 5 is increasing or decreasing by analyzing f prime of x, both algebraically and graphically. Justify your responses. So what we have here is the equation of a function. We don't have the graph of the function, so we can't simply look at the graph of f of x and just say, oh, this is where f of x is increasing, like we did in the first example, because we don't have the graph of f of x. Moreover, we're being told to find these intervals by analyzing f prime of x, because ultimately what we must do is we must find where f prime of x, the derivative, is greater than 0, and where f prime of x is less than 0. Because we know wherever the derivative is positive, the original function f is increasing, and wherever the derivative is negative, the original function f is decreasing. All right, so this is the goal here. Find where the derivative is positive and the derivative is negative. So the first thing we're going to do is we're going to solve this algebraically. And to solve this algebraically, we are going to need to find the derivative. So f prime of x by the power rule is 12x cubed minus 12x squared minus 24x. So this is my derivative, and again, I want to know where is the derivative positive and where is the derivative negative. All right, so here, in order to figure out where a polynomial is positive or negative, we algebraically are going to need to create a sign chart. So we're going to need to find where is the derivative equal to 0 in order to find the x-intercepts, essentially, to put on the number line. So really what we're doing here, if we set the derivative equal to 0, we're finding the critical values, right? And again, connecting back to what we just looked at a minute ago, well, where can a function switch from increasing to decreasing? It can switch at a critical value. And so that's why we need to find those critical values by setting the derivative equal to 0. So I'm going to factor out a 12x, and I'm left with x squared minus x minus 2. And that quadratic factors to x minus 2 times quantity x plus 1. So we're going to go ahead and say that our critical values are x equals 0, x equals 2, and x equals -1. So these are potential places where the derivative is switching from positive to negative, right? Critical values is where the derivative is equal to 0, so it's where the derivative is potentially switching between positive and negative, therefore where the original function is potentially switching between increasing and decreasing. So what we're going to do is determine if there is a change in sign by doing a sign analysis. So we are going to go ahead and take the domain of the original function f of x and put that on a number line. So I'm going to go ahead and put -infinity to infinity on a number line. That's the domain of f of x, all real numbers. And I'm going to put the critical values on the number line in order from least to greatest, -1, 0, and 2. And then I'm going to pick test points, test values, in each interval. So between -infinity and -1, I'm going to pick -2. Between -1 and 0, I'm going to pick -1/2. Between 0 and 2, I'm going to pick 1. And between 2 and infinity, I'm going to pick 3. So what we're doing is we're taking these test points and we're going to plug the test points into f prime of x. So we are interested in the sign of f prime of x. So we're doing a sign analysis, a sign chart, to determine the sign of f prime of x. Because if the derivative is positive, then the original function is increasing or decreasing. So that's going to tell us whether f is increasing or decreasing, question mark. Okay, so when I plug in -2 into the derivative, now I would always suggest plugging the test values into the most factored form of the derivative. So we're plugging it into f prime of x, so that's 12x times x minus 2 times x plus 1. That's where we're plugging -2 into. And so again, I'm really just focusing on the sign. I don't want to do any more work than I have to. So when I plug in -2 into 12x, that's going to give me a negative value. So this is how I do my sign charts. The way your former instructor may have had you do them might be slightly different, and that's okay. So here, 12 times -2 is negative. -2 minus 2, so I'm focusing on this middle piece. That's going to be -4, or ultimately just negative. That's all I care about. And then -2 plus 1 is -1. It's also negative. So a negative times a negative is a positive, and a positive times a negative is a negative. So this interval overall is a negative interval. So we picked a test point, -2, but that test point represents what's happening over the whole interval. So from -infinity to -1, f prime, the derivative, is negative on that interval. If the derivative is negative on that interval, then f, the original function, is decreasing on that interval. F is decreasing on that interval. And then we move on and we check the next test point value to see what's happening on the interval from -1 to 0. So I plug in -0.5. 12 times -0.5, that's negative. -0.5 minus 2, also negative. But -0.5 plus 1 is positive. So this time, this entire interval is a positive one, meaning that f is increasing on that interval. So the sign of f prime was positive, means that f is increasing. And we just keep moving on down. So if I plug in 1, 12 times 1 is positive this time. 1 minus 2 is negative. 1 plus 1 is positive. So overall, I'm going to have a negative interval. And if f prime is negative, f is decreasing. And when I plug in 3 times 12 is positive. 3 minus 2 is positive. And 3 plus 1 is positive. For an overall interval where the derivative is positive, meaning the original function is increasing. So ultimately, we wanted to find where's the derivative positive and where's the derivative negative. So we found the derivative. We needed to set it equal to 0 so that we could create a sign analysis using those zeros, right? Like those x-intercepts. They have a special name. When you set the derivative equal to 0, you're finding critical values. So we put the critical values on a number line. That number line has to represent the domain of the original function. So that's all real numbers. We pick test points in each interval. We plug those test points into the derivative. We want to know where's the derivative positive and the derivative negative, because that will tell us whether f is increasing or decreasing. Now this sign chart is just scratch work. So what we want to be able to do is summarize our results and justify our responses. So down here, there's a little space to do that. So what did we learn? F is increasing on the intervals from -1 to 0, and also, so right here, -1 to 0, and also from 2 to infinity. And intervals of increasing, decreasing are always open, right? And the reason why we know this is because, I'm going to have to squish this in here, because f prime of x was positive on those intervals. That's the key, because the derivative was positive. And then we learned that f of x is decreasing. The original function is decreasing on the interval from -infinity to -1, and also on the interval from 0 to 2. So those two intervals are where f is decreasing, and we found that was because f prime of x was negative on those intervals. All right, now before we move on from this example, the second part of the question said, by analyzing both algebraically and graphically. Now in general, you're not going to have to do each problem in both ways. I just want to show how in this particular example we could have done this problem graphically. Now, by that, I don't mean graphing the original function. So we want to graph the derivative function. So we still have the same goal. We must find where f prime, the derivative, is positive and where the derivative is negative. This time, though, we're going to do it graphically. Now, the derivative is still the same function, and we're actually still going to set the derivative equal to 0 in the same way that we did previously. So we're going to have to factor it completely, and we're still going to have to get out these critical values. But we're going to want to then make the connection to the fact that if these critical values were found by setting the derivative equal to 0, these are x-intercepts of the derivative. When you set a function equal to 0 and you find x values, those x values are x-intercepts of that function. So instead of creating a sign chart to determine where is the derivative positive or negative, we could instead just graph the derivative. We have the x-intercepts, so the x-intercepts are 0, +2, and -1. All right, so these are my zeros. And so again, I'm graphing the derivative. Well, an x cubed function with a positive leading coefficient, a cubic with a positive leading coefficient, has end behavior with the right side pointing up and the left side pointing down. And then each of these x-intercepts has a multiplicity of 1. So if you factor this completely, as we did, we can see that each x-intercept came from a factor with a multiplicity of 1. And when that happens, the graph cuts through the x-axis at each of those x-intercepts. So I'm going to cut through -1, I'm going to cut through 0, and I'm going to cut through 2. So that's all some pre-calculus review. Right, so what I have graphed here is I have graphed f prime of x. I've just graphed the derivative. Remember what we wanted to do. We must find where the derivative is positive and the derivative is negative, because that will tell us where the original function is increasing or decreasing. Well, we did a quick sketch of the graph of the derivative using our pre-calculus knowledge of graphing higher degree polynomials that are factored, and we can see that the derivative is positive or above the x-axis from -1 to 0 and 2 to infinity, which are the exact answers we got for where f is increasing, and then f is decreasing where the derivative is negative, or in this example, below the x-axis. So below the x-axis from -infinity to -1 and 0 to 2. Now, I will say most of the functions that we are going to deal with are better evaluated, better solved using a sign chart, only because the graph of the derivative isn't always this easy. So this would be considered an easy, quick polynomial to sketch if we remember our pre-calculus rules. But a lot of the derivatives that we're going to get are not going to be functions that we can easily graph just kind of on the fly like we just did. But for this example, we kind of had the choice of doing either one, and I wanted to show that ultimately either one is an option if you can graph the derivative easily. On this next example, we want to find the intervals on which f of x equals sine x plus cosine x is increasing or decreasing on the interval from 0 to 2 pi. So here, the original function f of x is sine x plus cosine x, and that's not a graph that we should, automatically be able to graph. The whole idea here is to find where f is increasing or decreasing. We are going to need to find where f prime of x is positive and where f prime of x is negative. So let's go ahead and start by finding f prime of x. So the derivative of sine is cosine x. The derivative of cosine is negative sine x. So we want to figure out where's the derivative positive or negative. Well, to do this, we're going to need to find the critical values, which is where is this derivative equal to 0, because that's where I could potentially switch from positive to negative, or f being increasing to decreasing. So here I'm going to set 0 equal to cosine x minus sine x. I'm going to add the sine x to the other side so that I can think about this as where does sine x equal cosine x, but specifically on the interval from 0 to 2 pi, which just means on the entire unit circle. So on the unit circle, where does sine x equal cosine x? What angles? So what angle do we plug into sine so that when we plug that same angle into cosine, we get the exact same value? Well, the obvious answer in quadrant 1 is pi over 4. So sine of pi over 4 is square root of 2 over 2, and cosine of pi over 4 is square root of 2 over 2. So that's the first obvious answer because it's in quadrant 1, but the other place where sine will equal cosine is in quadrant 3, where both sine and cosine are negative. So the angle in quadrant 3, that would have a reference angle of pi over 4 would be 5 pi over 4. So this is just like really knowing the unit circle here. So we're talking about like this coordinate point when you plug in 5 pi over 4 is positive rad 2 over 2, positive rad 2 over 2. And then down here, when you go all the way to 5 pi over 4, this is negative rad 2 over 2, negative rad 2 over 2. So the sine and cosine values, the x and y values, are the same in quadrants 1 and quadrant 3 at pi over 4 and 5 pi over 4. So that being said, these are my critical values. So this is where, again, the derivative is equal to 0, and this function would not be undefined, so it's just setting the derivative equal to 0 in this case. And then we're going to go ahead and create our number line with the domain. Now we're given a restricted domain here, the interval from 0 to 2 pi. So we're going to break that up at pi over 4 and 5 pi over 4. And we're going to go ahead and pick some test points in each interval. And remember what we're going to do with those test points. So we're interested in the sign of f prime. Well, f prime of x is cosine x minus sine x. So we are going to need to pick test points that we can plug in to the derivative, cosine x minus sine x. So they better be angles on the unit circle that we know the values of. So we're going to pick here pi over 6, between pi over 4 and 5 pi over 4. I think one of the nicer options is going to be one of the quadrantal angles, right? So like pi over 2 or pi, doesn't really matter which one. We'll go with pi. And then between 5 pi over 4 and 2 pi, right, the rest of the way, there's one quadrantal angle here. That's 3 pi over 2. I think that would be the other sort of nice value to choose. All right, so now we're going to plug those test points into cosine x minus sine x so that we can see whether the overall sign would be positive or negative. So here we have cosine of pi over 6 is the square root of 3 over 2. And then sine minus sine of pi over 6, that's 1/2. Well, that's going to be a positive value. So radical 3 is bigger than 1. So this is going to be a positive interval overall. You didn't have to necessarily write out the values if you could just think about that in your head, but you could. And then if you plug in pi into cosine of pi is -1. So we have -1 minus, and then sine of pi is 0. So we have -1 minus 0, that's negative overall. And when you plug in 3 pi over 2 into cosine, that's going to give us 0. And then minus sine of 3 pi over 2. So the y value down here is -1. So I have 0 minus -1, which is +1 or positive overall. So the sign of f prime alternates positive, negative, positive. Now just a quick thing, that doesn't always happen. I know in the 2 examples we did together, the signs alternated each time. That's not always the case, so you do have to test each test point, each interval for the sign of f prime. And then that's going to tell us about whether f is increasing or decreasing. So if the derivative is positive, f is increasing here. If the derivative is negative, f is decreasing. And if the derivative is positive, f is increasing. Okay, so now we have our answers, but we have to actually pull the information, extract it from the chart, because the chart is just, as I said earlier, sort of our scratch work. So here's what we have concluded, right? F is increasing on the interval from, on the x value interval from 0 to pi over 4. And actually, I don't know why I put a close bracket. We're doing intervals of increasing and decreasing, so we can just always say open intervals. So 0 to pi over 4, and I also don't know why I put union, because we don't want to do that. From 0 to pi over 4, and from 5 pi over 4 to 2 pi, because that's where f prime was greater than 0, right? So that's because, just shortened it to b/c. And then f is decreasing on the x interval from pi over 4 to 5 pi over 4, because that's where f prime is negative. Right, so we want to be able to summarize our results, say that we understand what is actually happening in this sign chart. You know, where is f increasing, where is f decreasing over these intervals, and this is the justification. Let's go ahead and explore the idea of concavity informally. A function is concave up on an interval if it is opening upward on that interval. A function is concave down on an interval if it is opening downward on that interval. So here I have an example of a function where we can see that this portion over here off to the left would be considered concave up because it's opening upward, as opposed to this portion over here on the right, which would be considered opening downward. Now there's a nice little way to help you remember the difference, and it rhymes. Concave up, like a cup. So think about how a cup would hold liquid in it and how this side that's facing upward, opening upward, could hold some liquid, versus concave down, which is like a frown. So if you're frowning, that shape is a concave down shape. Then we also have this idea of a point of inflection. So we say that c, f of c is an inflection point of f of x if f of x is continuous at x equals c and the concavity changes at x equals c. So this point here that's been sort of accentuated and made a little bigger is an inflection point because the function is continuous there and there is a change in concavity from concave up to concave down at that point on the function. Let's go ahead and look at an example that doesn't include any calculus. The following is the graph of f of x. So we have just the original function we're looking at, f of x, and we're asked to identify the intervals of concave up and concave down of f of x and inflection points of f of x. So what I'm going to do is just go ahead and start to look at this function and identify any intervals of concave up first. So concave up intervals, I'm just going to highlight them here, right? Anything that looks like a cup, anything that's opening upward. So I have these two portions here would be concave up, and then over here I also have another concave up interval. So now I'm going to go ahead and describe those intervals across their x values, just like I would for increasing, decreasing intervals. And similarly, for increasing, decreasing intervals, we use open intervals. The same thing applies for concave intervals. So f is concave up on the interval from a to b. We're also concave up on the interval from b to c. So again, an open interval. And I'm concave up on the interval from d to infinity, right? From d to infinity. So here are our concave up intervals. Now let's talk about where f is concave down. So we started concave down if we look to the far left, and then we're also concave down over here in the middle-ish. So we're going to describe those intervals as x intervals. I'm concave down from negative infinity to a. So we have negative infinity to a, and I'm also concave down from c to d. Now the last thing we're being asked is to find the inflection points of f. So the inflection points of f are those values where concavity changes there, but the function also has to be continuous at those locations to be considered inflection points. So we can see a change in concavity is happening at the x value a. It would change from concave down to concave up, and I'm continuous there. So at a, f of a, that would be an inflection point. So since they're coordinate points, we want to include the x and y value. So it would be a, f of a. B would not be considered an inflection point because there's no change in concavity there. I stay concave up. Now at C, there is a change in concavity. I have a change from concave up to concave down. However, we do not have continuity at x equals c. So we do have this infinite discontinuity that's happening there. So C would not be considered an inflection point. Finally, we have at D, there is a change in concavity from concave down to concave up, and the function is continuous at D, so that would also be an inflection point, D, f of D. Now let's go ahead and more formally define concavity. Let f of x be a differentiable function on an open interval from a to b. Then f of x is concave up on a to b if f prime of x is increasing on a to b. and f of x is concave down on a to b if f prime of x is decreasing on a to b. Now let's go ahead and take a look at this image for a second and try to make sure we understand what's happening in this sort of formal definition. So we can see here that this function starts out as concave down. But what I want to do is I want to analyze some slopes of tangent lines on this portion of the graph that I can clearly see is concave down. So here I have a couple of little tangent lines, and I want to just approximate some slope values for these tangent lines. So I know there's no numbers here, but let's just say that the slope of this tangent line right here is positive 1/2. I do know that it's a positive value. Let's say the slope of this tangent line right here on the very top is 0 because it looks perfectly horizontal. And then the slope of this tangent line here is some negative value. So let's say maybe -1. So as I look from left to right, the slopes of the tangent lines are decreasing. The slopes of the tangent lines are decreasing. So I'm going to go ahead and write that down. Slopes of tan lines are decreasing. The slopes themselves are getting smaller. Well, anytime we see this slope of a tangent line, that's equivalent to a derivative. So in order for a function to be concave down, for f of x to be concave down, its slopes of tangent lines, its derivatives, have to be decreasing. That's exactly what this says right here. For f of x to be concave down, we need f prime of x, the derivatives, the slopes of tangent lines, to be decreasing to form this opening downward shape. And then similarly, let's look at the concave upside. And again, if we just approximate these slopes of these tangent lines, so let's go ahead and say this is like -1/2, and then the horizontal one is 0, and this one looks a little bit steeper, like maybe 2. If we look from left to right, how would we describe what's happening to the slopes? Well, they're getting bigger. I go from a negative to 0 to positive. So this time we have slopes of tan lines are increasing. So again, slopes of tangent lines are derivatives. So f prime has to be increasing for my original function to be concave up. All right, so that's where this formal definition is coming from. Now let's kind of extend this a little bit further. How would we determine where f prime is increasing? In the previous section, we said this, that f of x is increasing if f prime of x was greater than 0. So we said f is increasing if its derivative, which would be f prime, is positive. So we can extend that. How would we determine where f prime is increasing? Well, that's where its derivative is positive. What's the derivative of f prime? F double prime. So how would we determine where f prime is increasing? We have to find where f double prime is greater than 0. And that's where the second derivative analysis is coming in. So what does f double prime, the second derivative, say about f of x? Well, let f of x be a differentiable function on the open interval from a to b. Technically a twice differentiable function, because we need to find the second derivative, so that word's missing. Then f of x is concave up on a to b if the second derivative is greater than 0 for all x in a to b. And f of x is concave down on a to b if the second derivative, f prime of x, is less than 0 for all x in a to b. So again, let's just try to make the connection one more time. So one of the things I observe is that when students just try to memorize these properties, everything gets jumbled together. But if you understand the concept and the relationship, then everything just becomes a lot more clear. So if the second derivative is positive, right? So if the second derivative is greater than 0, then we know that f prime is increasing. f prime is the slopes of tangent lines. So if the slopes of tangent lines are increasing, so think a negative slope, 0, a positive slope, then what shape does that create if those are all tangent lines? That's going to create this upward opening shape, opening upward shape. So that's concave up. Versus if the second derivative is less than 0, then f prime is decreasing. If f prime is decreasing, that's slopes of tangent lines are decreasing. So that means that I'm going to have some positive slope, let's say 0 slope, and then some negative slope going on. So again, if those are slopes of tangent lines at some point, and I create a curve where those are the tangent lines, that curve is going to be concave down. So where might f of x switch between concave up and concave down? Well, it might switch when the second derivative is equal to 0 or when the second derivative does not exist. And we don't have a special name for these in the sense that when the first derivative was equal to 0 or did not exist, we called those critical values. Well, here what we do is we call these possible inflection point values because we don't know for sure that there will be a change in concavity there unless we test the intervals and find out. Let's take a look at an example. Find the intervals where f of x equals 3x to the 5th minus 5x to the 4th plus 1 is concave up or concave down and points of inflection of f. So to find where f is concave up or concave down, we need to find, so we must find where f double prime of x is greater than 0 and where f double prime of x is less than 0. So in other words, we need the second derivative. So let's proceed. We'll find the first derivative first, of course, using the power rule. That's 15x to the 4th minus 20x cubed. And then we're just going to move on to take the second derivative. F double prime of x is 60x cubed minus 60x squared. So this right here is my second derivative. I want to know where is the second derivative greater than 0 and where is the second derivative less than 0. Well, what we're going to need to do is figure out where the second derivative is equal to 0 so that we can use those values to create our sign chart analysis. So we're going to set this equal to 0. 0 is equal to 60x squared times x minus 1 in parentheses, so I'm factoring it. And then if I set each piece equal to 0, I'll get x equals 0 and x equals 1. So what have we just found here? These are not called critical values. That's where the first derivative is equal to 0 or undefined. So here, the only thing we can really call these are possible inflection point values. Sometimes to shorten it, you might see me write PIP for possible inflection point. But other than that, they don't really have a special name. So we're finding where the second derivative is equal to 0 or undefined, and then we are going to take those values and split up the domain of the original function using these values. The domain of a polynomial is all real numbers. So here's my number line from negative infinity to infinity. We're going to plop 0 and 1 on there. And we are going to pick some test points. So let's say -1, 1/2, and 2. But this time, because we're interested in the concavity of f, we are going to take these test points and plug them into the second derivative. So what we want is the sine of f double prime. And I would choose the most factored, simplified version of f double prime to plug our test points into. So we're going to find the sine of 60x squared times x minus 1. That is what we're going to plug our test points into. All right. So here, if I plug in -1 into x squared, if I plug anything into x squared, that's going to give me a positive. So that's kind of nice about this first piece, this first factor, it's always positive. So our sign analysis is going to look like a positive times a negative. Negative 1 minus 1 is negative. So overall, this first interval is negative. Now, if the second derivative is negative, that tells me about the concavity of f. So this is going to tell me whether f is concave up or concave down. Well, if the second derivative is negative at this test point at -1, then that means that the entire interval is such that the second derivative is negative, meaning that f is concave down on that interval. And then we just keep going. We plug 1/2 into each factor of the second derivative. Again, the first part is going to be positive all the time. 1/2 minus 1 is negative. So we end up with another negative second derivative interval between 0 and 1. So on that interval between 0 and 1, I'm still concave down. And then finally, if I plug in 2, again, 60x squared, doesn't matter what I plug in, is positive. 2 minus 1 is positive. A positive times a positive is positive. So this final interval from 1 to infinity is going to be a concave up interval for f. So let's go ahead and summarize those results here. So I can say that f is concave up on the x interval from 1 to infinity because f double prime was greater than 0 there. And then we can say that f is concave down on the interval from -infinity to 0 and also on the interval from 0 to 1 because f double prime was negative. Now the last thing to do is to find inflection points. Now these x values, 0 and 1, were possible inflection points, or the x value of the entire point, but we don't know that they're actual inflection point x values unless concavity changes there. Well, at 0, there was no change in concavity. The function f stayed concave down. But at x equals 1, concavity changed on f from concave down to concave up. So that means at the x value 1, there is an inflection point. But an inflection point is an entire coordinate point. It's, again, like an x comma y. So in terms of inflection points, I'm going to switch colors here. So the inflection point of f is 1, f of 1, right? It's a point on f. So the x value is 1, the y value is whatever happens when you plug 1 into the original function. So when we plug 1 into the original function up here, right, so I'm going to do this work up here because that's where I have space, it's really just 3 minus 5 plus 1. So that's -2 plus 1, which is -1. So my inflection point is 1, -1. In this next example, we have two parts. We have find and justify the intervals where f of x equals e to the arctangent x is A, increasing or decreasing. So first we're going to start with where is f increasing or decreasing. And let's remind ourselves that that means we need to find where is f prime positive and where is f prime negative. So we're going to need f prime, we're going to need the derivative. So f prime of x is equal to e to the arctangent x. So this is a chain rule. E to the arctangent x times the derivative of the inside. Well, the derivative of arctangent is 1 over 1 plus x squared. So here, this is, I'm going to write it as e to the arctangent x over 1 plus x squared. Now, what we would need to do at this point is to attempt to set this equal to 0 and find where it's undefined to find any critical values to create my number line. But we're going to run into a bit of a problem when we try to do that. So when I have a quotient, I would think about, trying to set the top and bottom equal to 0. So if I try to set, if I try to set the top equal to 0, e to the arctangent x equal to 0, I find very quickly that that's not possible. In an exponential function, the outputs are always positive. So if I try to set this equal to 0, like question mark, that's not possible because e to the arctangent x is always greater than 0. So that means there are no solutions to the derivative being equal to 0. Well, in a quotient, that quotient is undefined, or the derivative is undefined if the bottom is equal to 0. So if we try that, if we try to set the bottom equal to 0, we find that that's not possible either, right? So question mark, no. And if we subtracted the negative, or subtract the 1 to the other side and take the square root of -1, we get imaginary values. Or we can hopefully also see how 1 plus x squared is always positive, because it doesn't matter what number you plug in. If you square it, it's positive, and then plus 1, it's positive. So any exponential, doesn't matter what exponent is up here, that's always positive, and then 1 plus x squared is always positive. So this quotient right here, turns out, is always greater than 0. So what does that mean? Well, it does mean that there are no critical values. But remember what we're trying to do, right? A lot of times people just memorize it as a set of steps. So they're like, okay, I took the derivative, now I find where's the derivative 0 and undefined. Oh, well, it's not, so I'm stuck. There's no answers here. But we're trying to find where is the derivative positive and where is the derivative negative. Well, we just did our analysis, and the derivative is always positive. So if there are no critical values, when we do our number line of the domain, and the domain of this exponential is all real numbers, there's just no critical values to put on here. But let's just say we pick a test point, any test point, like 0. Well, we just said, doesn't matter what value you choose, the output's always positive. So what's the sign of f prime in this case? E to the arctan x over 1 plus x squared. It's positive. It's positive every time. If there are no critical values, then that means that the derivative is either always positive or always negative. So here the derivative is always positive, which tells us that f is always increasing. So the answer to part A here is that f is increasing on x values from -infinity to infinity, because that's where f prime is positive, right, over the whole entire number line. Now we're going to continue this example using the same function, but we're being asked to find where is that function concave up or concave down, and points of inflection of f. Now concavity has to deal with where the second derivative is positive for concave up, and the second derivative is negative for concave down. Well, here is our first derivative from part A, e to the arctan x over 1 plus x squared. And if I'm interested in the second derivative, I'm going to need a quotient rule. So f double prime of x is equal to low 1 plus x squared d high. Well, earlier we said the derivative of e to the arctan x was the same thing times the inside's derivative, 1 over 1 plus x squared, low d high, minus high e to the arctan x d low, the derivative of 1 plus x squared is 2x, all over the bottom squared, 1 plus x squared quantity squared. And we can cancel out 1 plus x squared over 1 plus x squared in that top left part of the quotient rule. And then on the top, we can factor out the e to the arctangent x that's in both terms of the numerator. So e to the arctangent x is factored out, and we'd have left 1 minus 2x, and then all over 1 plus x squared squared. Okay, so now this is as simplified as it can be, and this is perfect for us to be able to find those possible inflection points, right? So if I want to try to figure out where this is 0 or undefined, I would attempt to set So now I'll do this. I'll put, where is this 0 or undefined? Well, it would be 0 where the top is equal to 0. We explored already how e to the arctangent is always positive, so this can't equal 0. But 1 minus 2x can equal 0. I'll get x is equal to positive 1/2. And then the denominator is a place where potentially this quotient can be undefined, but again, this is always positive. 1 plus x squared, and then we're squaring it, so it's definitely positive. So right here, 1/2 is my only pip, my only possible inflection point. And so with that value, we're going to create our number line for our analysis of where the second derivative is positive or negative. So we have negative infinity to infinity. We break it up at 1/2. We'll pick some test points, 0 and 1. And we're interested in the sign of f double prime. And again, I would definitely plug it into the most simplified version of f double prime. So we're looking at e to the arctan x 1 minus 2x over 1 plus x squared squared. And that's going to tell us, the sign of f double prime will tell us whether f is concave up or concave down. Now we want to be as strategic as possible to do less work. So when I plug in 0, keep in mind that e to the arctan x is always positive, and the denominator, 1 plus x squared all squared, is always positive. So I truly only have to plug my test points into 1 minus 2x. So if I plug in 0 into 1 minus 2x, I'm going to get 1, which is positive, meaning that f is concave up. And if I plug in 1, 1 minus 2 times 1, 1 minus 2 is negative 1, so I get a negative interval. So I'm concave down past 1/2. And so my analysis is going to be that f is concave up on the interval from negative infinity to 1/2, because that's where the second derivative is positive, and f is concave down on the interval from 1/2 to infinity, because the second derivative is negative there. The final thing to do is to figure out what the point of inflections are, or points of inflection, and there's only one. 1/2 was a possible point of inflection, but because concavity changes there, and we know that at 1/2 I would be continuous, so e to the arctangent is a continuous function. On our previous example, we had a polynomial, also a continuous function. So we do have an inflection point at the x value 1/2, and then we'd have to plug 1/2 into the original function to get the y value of the inflection point. So I'm going to make some space here. So my inflection point of f is 1/2, comma, e to the arctangent of 1/2. So remember, it has to be a coordinate point. This was the x value. To get the y value, I plug it into the original function. It's an inflection point on f. Now, arctangent of 1/2 cannot be evaluated without a calculator. So there's only very specific values we can evaluate without a calculator on arctangent, like arctangent 1 or arctangent radical 3. This isn't one of those values, so we can leave our answer exact like this.